Stepped Impedance 3dB Ripple Low-Pass Filter by Sam, Kenny, and Jordan. Our specifications for this project was to design and build a stepped impedance 3dB low-pass filter with a cutoff frequency of 4 GHz, normalized to 50 ohm ports with an attenuation greater than 20 dB at 5 GHz. To start off our low-pass prototype, we use a magnitude of omega over omega c minus 1 to get 0.25. We then used Pulsar's 3dB ripple graph and plotted the value of 0.25 on the x-axis to find an intersection of at least 20 dB, which we found to be at n equals 5. Using table 8.4 from Pulsar, we were able to find the G values where n is equal to 5. With the following G values and by scaling the frequency to 4 GHz and impedance by 50 ohms, we calculated the capacitance and inductance value of the lumped elements for the low-pass prototype. The schematic was then designed in Microwave Office. The simulation of the low-pass prototype shows a 3 dB ripple in the passband with a corner frequency of 4 GHz as expected. It also shows an attenuation of negative 24 dB at 5 GHz. We then converted the low-pass prototype to an ideal transmission line model. From the plot, we can see that the filter still holds a clear 3 dB ripple in the passband and a cutoff frequency of 4 GHz, but the attenuation at 5 GHz came up a little, but still yields an attenuation close to 18 dB.
We used the impedance, operating frequency, and electrical length values from the ideal T-line design and inputted them into the TX line calculator on Microwave Office to obtain the values for the Microstrip line design, and also identified the substrate as a 62 mil Duoroid 5880. The simulation for the ideal Microstrip design still held the cutoff frequency at 4 GHz, and the attenuation at 5 GHz was similar to that of the ideal transmission line design. Following the HK principle of slowly adding complexities to the problem, we added the M-step element in the design in between each M-line element to represent the discontinuities found when the width of the microstrip has changed. The simulation of the uncompensated microstrip design shows a shallower ripple in the passband, and the passband also got a little bit shorter with a cutoff frequency at around 3.3 GHz. After compensating for the discontinuities, the defined ripple in the passband came back, but the cutoff frequency still remained at around 3.3 GHz. Here's a look at the stepped impedance low-pass filter layout that was made on Microwave Office. We exported this layout and began the fabrication process. Jordan will now explain how we built the filter.
Thank you, Kenny. Now, we started off the fabrication process by uploading our 1-to-1 DXF layout of our low-pass filter into the Silhouette program in Wayne's lab. Then we welded and scaled our filter to size. The recipe process starts with a piece of copper tape, putting it on another piece of packing tape, turn it over and place it on the Silhouette mat, using more tapes to hold it in place to prevent any movement during the cutting process. This is what it looks like when you turn it over. Next, we carefully lined up the mat with the Silhouette cutter and then press print. Then we carefully peel away excess copper and place it on Duoroid 5880. Next, we solder on the SMA connectors, starting from the side that has our copper tape, then the back side. Before taking measurements of the filter, we first need to calibrate the network analyzer. Then, we connect our low-pass filter to the network analyzer.
After taking measurements of the filter, we compared the values to the simulation we did on Microwave Office. We noticed that the trend of the plots are similar, but the cutoff frequency for a fabricated filter came up shorter at around 2.4 GHz. Although our filter provided a decent 3 dB ripple in the passband and a steep attenuation, did not perform how we tried to design it to be. We noticed that the copper wasn't cleanly cut at the edges, especially when the width became small. Imperfections from the fabrication process may have caused the filter to not perform like how we wanted it to.